Hi, welcome to my video on linear programming. In this video, we discuss a linear programming technique. We basically look at a brief description of what linear programming technique is, and we also look at how we can formulate a linear programming model, and we finally look at how we can solve a linear programming problem, particularly using graphical method. Now, linear programming is a mathematical technique which is concerned with the optimum allocation of scarce resources. It outlines the procedure of optimizing a given value that we call an objective function when the resources involved are subject to some constraints. Basically, the structure of a linear programming problem from this definition consists of two major components. So we are talking of an objective function as one of the major components in a linear programming problem. And the other one is constraints. So these two components are so key in linear programming, and we need to understand them. And so the objective function, which is always a linear function of the variables and that we are discussing or seek to actually determine, is usually a linear function, and the objective function is always of either maximization or minimization kind. And so when an objective function you find is a maximization, it will always be either to maximize a given output, to maximize some given sales, or to maximize the profits, and so on. But it can also take the form of minimization. If we are talking of minimizing maybe the cost of production or minimizing the loss and so on. So the word optimization here is simply getting the optimal solution or the best outcome from given alternatives. And then the other component is constraints. And so constraints are simply restrictions or limitations. And so as you try to get the best outcome, you have constrictions or that you have restrictions that you have to fulfill or to work within. And so they kind of guide this objective function. And so the constraints could be examples, could be maybe the maximum resources available. Resources could be in terms of maybe the labor available, the time available, or the inputs required, or any government restrictions or trade agreements. Those are some of the examples of constraints that you have to fulfill even as you seek to find the best alternative. So we now look at how do we then formulate a linear programming model having known what linear programming technique is all about. The procedure follows about 4 steps, and they have to be followed sequentially whenever you're formulating a linear programming model. The first step is always to define the decision variables. And the decision variables are mostly defined using letters, say x1, x2, and so on, depending on the number of decision variables in the problem at hand. And then we have the objective function, which needs to be defined. Once you have defined your decision variables, you now define your objective function, which is always a function in terms of the decision variables that you have defined. And you have to specifically also mention whether it is a maximization kind of objective function or of minimization kind. And then we have the resource constraints. So resource constraints have to be defined once you have defined the objective function. The resource constraints, normally they are expressed as inequalities, or can also be expressed as equations. So you'll find that the constraints are normally expressed as inequalities as equations, and they also express in terms of the same decision variables we have stated early. Then we have the non-negative constraints. Again, so non-negative constraints here, we are just setting the decision variables we have in stage one to be greater or equal to 0. For example, saying x1 is greater than or equal to 0, x2 greater than or equal to 0. The assumption here is that with linear programming problems, we do not get the quantities, because this x1 is meaning quantities of the number of products. Those number of products or units of a product can never be assume a negative value, and that's why we always include these particular constraints. So I have two examples here that we want to look at that shows a formulated linear programming model. The first one is a linear programming model that has been formulated, and this one has only two decision variables. And so this is actually our objective function, z equals to x1 plus x2. And we can see it's actually a maximization kind of objective function. And then subject 2, so these are now the set of constraints that we want to achieve that objective function by fulfilling these particular requirements. And so the first two constraints are actually the resource constraints, and the last two are the negative constraints. The second example illustrates a linear programming model that involves three decision variables, and again is a maximization kind of objective function. And the constraints here are 5, with 2 being resource constraints and 3 being negative constraints. So these are examples of linear programming models. And so you have emphasized that it is not always the objective function being maximized. You may also get one that talks of minimize given function z equals, let's say, 2x1 plus even 3x2. So it's not a must that it will always be maximization kind of objective function. Now, once we know how to formulate a linear programming model, or once we have a linear programming model that has been formulated like one above, the next stage we always move to is now solving that linear programming model. And in this video, we are looking at the graphical method. And the graphical method is only limited to solving linear programming models with only two decision variables. And the stages when you are followed when you adopt using graphical method is that the first one, we formulate the linear programming model like the one we have above. Then we plot the constraints with an intention that we get a unique region that we call the feasible region. Then use that particular feasible region to get the optimal value of the objective function. We have a case example here that I want us to look at. The example says a businesswoman is preparing cakes for sale. She has 8 eggs and 10 cups of sugar. She makes 2 types of cakes. Type A requires 6 eggs and 2 cups of sugar, while type B requires 12 eggs and 3/4 cups of sugar. If type A cake sells at 30 shillings, while type B cake sells at 40, you are asked to formulate a linear programming model, then use the graphical method to determine how many of each should she bake to realize the highest possible sales. So before even we try to define the decision variables, we may want to structure this kind of narrative in this form. If I may call these cakes, because you're having 2 types of cakes, type A and type B. and I have the first resource being eggs, and the second one being cups of sugar. So that then I have a table of this form where we are talking type A requiring 6 eggs and 2 cups, and type B requiring 12 and 3/4. But then we have what is available to use. There are only 8 eggs available, and there are 10 cups of sugar available. So from this, we can be able to begin by defining our decision variables. And so if we let x1 to represent the number of type A cakes that were to be sold, and we let x2 to represent the number of type B cakes, then we can simply see that if a type A cake is to be sold at 30 shillings, so to sell x1 cakes, x1 such cakes will be now 30x1 shillings, and to sell type B cakes would now be 40x2 because each cost will be sold at 40 shillings. And so the objective function will be the maximize z, which is equals to the sum of 30x1 and 40x2. So this becomes the objective function which has to be achieved subject to. Now the first constraint here will have to do with eggs, where we'll be looking at the eggs for making type A cakes plus eggs for making type B cakes should not be more than 80. And that's why you're saying 6x1 plus 12x2 should either be equal or less than 80. And similarly, when we look at the cups of sugar, again, 2x1 plus 3/4 x2 should be less than or equal to 10. So those are the resource constraints. Then we now include the negative constraint, where we are saying the number of type A cakes and the number of type B cakes, and they should be non-negative. It can only be 0 or more. And so if you want to use now graphical method, because this is now part A of the question where we have formulated a linear programming model fully, we define the decision variables, then we wrote the objective function and the constraints. So we do the graphing, and graphing here requires that we just graph the constraints only. That is what is required for us to plot. And so we plot these 4 inequalities in a Cartesian plane. And so when we plot them, we'll find that this is the line 2x1 plus 3/4x2 less or equal to 10. And the other one will be 6x1 plus 12x2 less or equal to 80. And so, of course, we have treated them as equations of straight lines so that we get the lines. But you see now, for each line to be converted into an inequality, we need to shade one side. For example, if we consider this, the red line of 6x1 plus 12x2 equals to 80, we pick a point either above or below the line. For example, if I pick a point like 0, 0, and substitute 0 for x1 and 0 for x2, you'll find that the left-hand side of this inequality will be 0 and less than or equal to 80. And so that means this particular point satisfies the inequality. And since it satisfies the inequality and is below the line, it implies that any other point below the line will also satisfy this inequality. And therefore, points above the line will now be treated like they are actually unwanted because they do not fulfill the equation of the line or the inequality, so therefore we shade them out. We shade them out. And then we go to the second line that we have also plotted, 2x1 plus 3/4x2 minus or less than or equal to 10. So if we may use the same again point like 0, 0, which is below the line, and substitute x1 with 0 substitute x2 with 0, you'll find that again 0 is less than or equal to 10. And so that still satisfies the inequality, or the inequality still holds. And so that means points below the line are actually satisfy the inequality, and therefore points above the line are treated to be unwanted, and therefore we shade them out. And then when you plot because this axis is x2 and this is x1. So if we look at this line as x2 equal to 0, and this one the same as x1 equal to 0. So if I want x2 greater or equal to 0, it means I'll be shading out this particular region, this negative side of the x-axis. And also, when you look at x1 greater than 0, we shall also be shading the lower side of this. And so we are getting this particular region that I'm calling R. So R is actually now the feasible region. So this is going to be the feasible region, and the region satisfied by all the inequalities. And so this region is the one that's going to provide us with actually the points that will give us the optimal solution of the objective function. The points we are more interested in the feasible region are the corners of the edges, like this corner, this point A, this point B, this point C, this point D, are mostly important for us in determining the optimal solution. And so we select those corner points and create a table of those coordinates of corner points. And remember the objective function here is to maximize 30x1 plus 40x2. So these are our points A, B, C, and D. So if I substitute these points, for example, a point like 5, 0, and you substitute in this objective function, 30 into 5 plus 40 into 0, you find that this is giving you 150. And so if you substitute all those points, those corner points, you get these solutions. And since the objective is to maximize the Z, then it means the maximum value of Z here is 290. Remember here, the Z here is actually implying the maximum cells. Z here is the maximum cells, which we are saying here is 290 from the cells of. And so 290 is achieved when x1 is 3 and x2 is 5. So in other words, we are saying this figure is obtained by selling 3 type AX and 5 type BX. So that's what it implies. And that's how you maximize that particular problem. The second example, which is more on minimization, talks of a salesman dealing with cameras and laptops. And he has been able to establish from experience that in order to maintain his sales, at least 120 items must be kept on display all the time. Of these items, at least 30 should be cameras and at least 60 laptops. If on average the cost of display for each camera is that, and that of a laptop is this, is a method to determine how many cameras and laptops that should be displayed to minimize the cost of display. So these are minimization. So if we define the decision variables, again, we can let x1 maybe to represent the cameras that to be put on display, and we let x2 to represent the laptops that should be displayed. So with that, we can now state our objective function, which I've said is minimization. So we minimize a z, which is now equal to this. Remember, the cost of displaying a single camera is 30 and a single laptop is 50. So we want to minimize that total cost. So it will be 30x1 plus 50x2. And this is only achieved subject to some constraints. And the first constraint has to do with the total number of laptops and cameras on display. In total should be at least 120. So the minimum should be 120. That's why you have that particular constraint. And then we have the other constraints that are on individual items. Like we have at least 30 should be cameras. So X1 should be greater or equal to 30. Again, at least 60 should be laptops. So X2 should be greater or equal to 60. Now, once you have inequalities of individual decision variables like this, these ones take care of now the non-negative constraints, in that you now don't need to plot or state even now X1 greater or equal to 0 and X2 greater or equal to 0. So this is our formulated linear programming model. And so we need to graph these three constraints on a Cartesian plane and be able to determine the feasible region. And so this is our line X1 plus X2. We want to make it an inequality more than that. You can see this point 120, the other one is 120. So if you pick a point below, like this point 0, 0, you can see 0 can never be greater than 120. So that means 0 is on the, actually on the unwanted side of the inequality, because it doesn't satisfy the inequality, and therefore any other point below the line does not satisfy the inequality. The other inequality here that we have is this particular inequality we are talking of. This is, remember, this is X2 and this is X1. So we are saying X2 greater or equal to 60. So the line X2 greater or equal to 60 is this particular line, and we are looking at values of X2 more than 60. It means we shall be shading the lower side of the line, so that we now have that. And lastly, we have this particular other inequality, which is talking of X1 greater or equal to 30. So that means the left-hand side of the line is unwanted. And so we have that. And so we are meaning this as now the required region, or rather the feasible region, which appears at least open-ended. And so we identify again the corner points in this particular region. You'll find this point, this point is, these are now the corner points. Okay, call this A, this B. This A is actually point 30, 90. And this B is actually point 60, 60. So those are the only corner points when you look at this particular representation of the inequalities. And so we use those 2 points to determine one that will give us the minimum of the objective function. So again, we have our results with the corner points A and B, and the objective function being minimized. To minimize that, we substitute again these coordinate points in the objective function. Point A gives us a figure of 5400. Point B gives us a figure of 4800. Remember, the objective here is to minimize the cost of displaying. So the minimum cost of displaying cameras and laptops from this is actually figure of 4800. And this is obtained when we are having 60 cameras on display and also 60 laptops on display. So that's how we use graphical method to solve a linear programming problem. Thank you so much, and thank you for watching.